We're going to begin our review here talking about forces going way back to the beginning of the second marking period. We're going to go through a few different kinds of forces and talk about what's important with those forces. So the first force we have is the force of gravity. So gravity is the force from Earth, or really any planet, but typically we talk about Earth acting on an object. And we're going to find the value of that force by doing Fg equals mg. The next force is the normal force, and that is the force we have from any surface. It always acts perpendicular to that surface, so the floor, the ground, etc. The one thing we want to keep in mind is do not assume that the normal force is equal to the force of gravity. That is sometimes true, but that will not always be true, and that's an important thing to keep in mind for force problems. Okay, moving on to friction. We have two kinds, if you remember. There's static friction and kinetic friction. So kinetic is going to exist whenever an object is sliding across a surface, whereas static is only going to exist if an object is not sliding. In terms of direction here, kinetic friction opposes the motion of the object, whereas static friction opposes the direction the object wants to move or wants to slide. So a lot of times with static, we want to think about which way the object would move or slide if there were no friction, and then friction will be going the opposite direction of that. The way we find them also differs slightly. For kinetic friction, the force of friction is equal to mu k, our kinetic coefficient of friction, times the normal force, whereas for static, that force of friction is less than or equal to mu s, our static coefficient of friction, also times our normal force. So the thing that I always keep in mind here is that mu s times the normal force, when we're dealing with static, is the max force of friction. All right? The actual force will be less than or equal to that, but that's the maximum force of friction. Moving on, not that this is an actual force, but it's a situation, and that is an inclined plane. And we had a little trick that we did here when solving inclined plane problems, and that was we would tilt our axis. So we would have a new x-axis that was parallel to our incline and a y-axis that was perpendicular. So if we imagined an object on that axis, right, the forces we would have acting on it, we would have gravity going straight down, as always, and our normal force going perpendicular to our surface. And there could be other forces, but these two will definitely always be there. And the key thing we're going to do here is we're going to break that force of gravity into its x and y components. Okay. Now we know that the angle theta here, the angle of the ramp, is the same as that upper angle there in the force of gravity triangle. So we can use that to break it into x and y components. So what we end up getting is this y component here is the adjacent side. That's going to be Fg cosine theta. And this x component is the opposite side. That's going to be Fg sine theta. So that's what our basic forces are going to look like. And obviously there could also be pushes, pulls, friction, etc. if we're dealing with an object on an incline. Moving on to springs here, we have our formula for the spring force, which is that the force of the spring is equal to k, our spring constant, okay, times x, the distance that spring is stretched or compressed. The one piece of important information I would say that's relevant here is we want to keep in mind that x is the change in the length of the spring, okay, not the actual length. This is the distance stretched or compressed, or the change in length. All right, last thing here, just a few general tips for solving these specific force problems. As you've heard me say many times this year, we always want to set up our max and may in order to solve them and draw our free body diagram. In addition to that, we're always going to find components for any force that's at an angle. And the last thing, which is always important, is thinking about signs. We know that signs are important, particularly with forces. We want to think about the direction of our acceleration. All right, moving on to multi-body problems, there's two things that we're always going to know when we have these problems. And the first is, and this really comes from Newton's third law here, but the forces between objects are always going to be equal. So maybe it is a rope connecting the two objects, maybe they're physically pushing on each other, but the key thing we know is that the forces that they exert on each other are going to be equal, and we know that from Newton's third law. The other thing that we're going to know typically is that the accelerations for the objects are also going to be equal, okay? And that's simply because the multiple objects, are moving as a system. They're moving together, so they have to be accelerating at the same rate. So solving these problems, when we do have multiple objects, like any other force problem, we're going to set up an F equals ma and free body diagram, but we're going to do it for each object in our system, okay? So each object in our system is going to have an F equals ma and free body diagram set up. While we're doing that F equals ma, the one tip that I would say, and you don't necessarily have to do this, but I think it's easiest if you make the direction of the acceleration positive. So whatever direction the object is accelerating, even if it's left or down, make that be the positive direction and go from there. And that's going to lead nicely into our next thing that we're almost always going to be doing for these problems, and that is we're going to add the equations, okay, that we set up. We're going to add them together. And when we do that, the forces between the objects should cancel when we go and add those equations, okay? And then the second thing that should happen is we should be left with the total mass of the system times that acceleration. All right, so the total mass of the system times whatever that acceleration is. One other thing to keep in mind here is sometimes it is useful to consider what we've called the systems method, okay, which is just another way of solving it. What we just talked about is always going to be perfectly valid, right? But with the systems method, we're going to treat all the objects as one object, okay? And when we do that, we're going to use the total mass to set up our F equals ma. All right, that's the first step in doing the systems method. And the second thing is we're only going to consider outside forces. So since we're only considering outside forces, that means that any forces between the objects, okay, are not going to count. So all those third law pairs that we talked about up here, we're not even going to worry about them because we know they're going to cancel out either way, and they don't cause the system to accelerate. So that is another way of solving it if you don't like the other method. All right, moving on here to circular motion, which is our next piece. First, let's talk about velocity and acceleration for an object in circular motion. So the velocity of an object in circular motion is tangential. So imagine we have an object going around like that. The velocity at any given point will be a tangent line to that circle. Our acceleration is going to be inwards, okay, or towards the center. And we talked about how that word centripetal, okay, that's the kind of acceleration we have, means center seeking or towards the center. We also have ways of solving for that velocity and for that acceleration. So the velocity of an object moving in a circle is given by 2 pi r over t, where t is the period, the time it takes to go around once, and r is the radius of the circle. The acceleration is given by the equation v squared over r, all right, where v is the velocity, the magnitude of the velocity for the object going in the circle, and r is the radius. Just one conceptual point here that we should clarify, and that is the difference between centripetal and centrifugal. Centripetal is the actual acceleration we have, that inward acceleration for an object moving in a circle. That also could be used to describe the force. Now, that other word, centrifugal, is that description of that feeling when you feel like you're being thrown out of a circle. And a lot of times it's referred to as a pseudo force, right? The real reason is Newton's first law. If we think about an object going in a circle, that object wants to continue moving straight, but in order to make it turn, we need some force going inward, pushing it in, keeping it moving in a circle. But when we experience this, we feel like we're being thrown out of a circle. All right, some tips here for solving these problems. We're really just doing force problems here. So we're going to set up F equals ma, just like we would for any force problem. The one thing that's different is we know our acceleration is given by that v squared over r. So we do have a new way of finding our acceleration and velocity for that matter when we're dealing with a circle. The other thing to think about here is for horizontal circles, okay, like the one I have here, a lot of times we use that side view, okay, where the object is kind of coming out of the page towards you, and it's traveling something like this. So it's coming out of the page and then back around. So we can draw our forces then based off of that. So gravity we know would be going down, and then depending on what the situation was, there would be other forces, but we don't necessarily know what they would be without knowing the situation. Moving on to banked curves here, and the trick with banked curves is actually not a trick at all, but when we do have a banked curve, we don't tilt our axis. This is different than an inclined plane, but there is a very important reason for this. If we have an object on a banked curve, and again, this is going to be that side view, okay, there's the center of our circle, our acceleration for that object is going to be inward, directly to the right, not at an angle at all. And so we don't want to tilt our axis because that actually complicates things. So we're going to leave it just the way it normally is. So gravity going straight down does not need to be componentized. However, our normal force now that's going up at an angle does need to be broken into its x and y components. All right? Much like gravity, the angle of the banking ends up being that angle there. And so the y component of the normal force becomes Fn cosine theta, and the x component becomes Fn sine theta. And if we're dealing with a banked curve without friction, this force, that horizontal component of the normal force, is what keeps it moving in a circle. We had a similar idea here when we had those conical pendulums, so the objects on strings going around in a circle. The only difference is instead of a normal force keeping it moving in a circle, it was a tension force, the x component of the tension force keeping it moving in a circle. Okay, moving on to projectile motion here. So projectile motion is simply a combination of x and y motion. And so the most important concept we need to know is what the motion looks like in the horizontal direction and the vertical. And in the horizontal direction, we know that the motion is constant velocity. Okay, and that results from the fact that there are no forces in the x, and therefore our x acceleration is 0. In the y direction, the motion is free fall. Okay, this is the exact same as the free fall we've studied earlier in the year. And our acceleration is 9.8 meters per second squared down. The other thing we need to know about are important concepts for the two different kinds of launches. The horizontal launch and the angled launch. So we're going to work through those concepts right now. So as always, we know our two accelerations, 0 and 9.8. We also know if it's launched horizontally, that means that it's not launched vertically at all. So we can say that our VIY equals 0. All right? So our initial velocity when it's launched is 0 if it's launched horizontally, and that's probably the most important concept there with a horizontal launch. With an angled launch, we know once again right off the bat our two accelerations, but we know a few more concepts here with an angled launch. One thing we can do with an angled launch is if we know that initial velocity and launch angle, we can componentize that. So, based on that initial velocity, our initial in the x, or VIX, is simply going to be VI times cosine of theta, and our initial in the y is going to be VI times sine of theta. We also know, much like free fall at the peak, our velocity is 0, but it's only the y velocity that's 0 at the peak. Okay, and that's true regardless of the situation. We also know our time here at the peak is half the total time. However, that is only true, okay, when it is symmetrical. Okay, so that one's only true when it's symmetrical. Additionally, we know when we return to level ground, our y displacement is 0. Our y velocity is the negative of our initial. Okay. We also can say, and this isn't something that we always talk about, but that our x velocity is just equal to our initial, right? Our x velocity doesn't change as we go throughout our launch. So our x velocity will always be that same amount there. All right, even though the y goes up to 0 there, then it's down there and even more down at the very bottom part. For solving these, we're going to set up two charts, one for the x direction, one for the y direction, as we've always done, just like kinematics, but 2 times. The next thing is we want to think about concepts that we know and when those concepts occur. All right. So it doesn't matter just what the concept is, but when it occurs. Is it at the peak? Is it when it returns to the ground, etc.? One other thing to keep in mind here with these is that time transfers, and what I mean by that is time can go from the x to the y because time doesn't have a direction. Alright, so universal gravitation was the next topic we talked about, and we know that gravity, on its most basic level, is a force that exists between all objects with mass. That is the key thing. Any two objects that have mass, whether they're enormous or really, really tiny, have a gravitational force between them. The way we find that force is Fg equals G m1 m2 over r squared. Okay, where m1 and m2 are the masses of the two objects, and that r squared, although you might think it's radius, it's really the distance between the objects. The other thing we talked about related to this was finding the acceleration due to gravity, little g, which we can do gm over r squared. So this would allow us to get what the acceleration due to gravity would be on a planet. Okay, if we plugged in the values for Earth, that would be 9.8. And so the r in this case is the distance between the location where you're finding g and the center of the planet. And I keep saying planet, but really it could be any object. It could be a moon, it could even be an asteroid or a meteor or something like that. So it's really a distance between the location or the object and the center of the other object. Some tips here for these problems, or for this in general. Okay, keep in mind that Fg and G as well are inverse square laws. Okay, so that means that as the distance doubles, all right, the force or the acceleration due to gravity is divided by a factor of 2 squared. Okay. The next thing is when we're dealing with those ratio problems, we need to set up two equations and combine. So those are the ones where, you know, the force of the gravity between two objects is F. What happens if the distance between them triples? We would set up our new and our original situation for those. And then lastly, and this goes back to what the meaning of R is. If we have a situation where we have some object at a height above the surface of a planet, moon, etc., okay, the R we care about is the distance from the center of the planet, moon, etc. to that object. All right, so that would be this distance here, which really ends up being the radius of the planet itself plus the height. So keep that in mind. All right, moving on to Kepler's laws here. Conceptually, we have three pieces we need to talk about. The first law tells us that all planets orbit in elliptical paths. This actually applies to any orbit. Any orbit is an elliptical path. The second law tells us that objects sweep out equal areas in equal amounts of time, but really what that means is that planets or other objects in orbit travel faster when they're closer to the central object. And this idea of traveling faster when closer we can actually explain a little bit now using conservation of energy. And the third law, conceptually, all right, tells us that the farther an object is away, okay, whether it's a planet or a comet or whatever, okay, the longer it takes to orbit, the longer the period is. All right, so if we're looking at our planets, the closer the planet is, like Mercury is the closest, that has the shortest orbit, and the planets that are much further away, like Neptune and Saturn, have much longer orbits because they're farther away. Mathematically, for that third law, we have two equations that we're going to use. The first is t squared equals 4 pi squared r cubed over gm. And we're going to use this when we're concerned about a single object. Okay, that's going to be the first thing that's going to be true. And when we know we're concerned about the mass of the central object. Okay, because that's what that m is. And that's an important point in this equation. That m is the mass of the central object. So if we want to find that, or we know that and need to use it, then that's our form of Kepler's law that we're going to use. The second way that we can do Kepler's third law is this ratio format, TA squared over RA cubed equals TB squared over RB cubed. This is going to be useful when we are comparing two objects orbiting the same thing. Okay, that's the time when we're going to use this. The advantage of this one, in addition to not needing to know the mass of the central object, we also can use any units for this one because it's going to cancel out as long as they're the same on both sides. So period could be in years or days or months or whatever, as long as it's the same. In terms of problem solving tips, the first one that seems to get mixed up a lot is that r is the radius of the orbit. Okay, not the radius of the sun or the planet or anything else, but the radius of the orbit or the average distance between the two objects. Okay, and we said this before, but I'll say it again here, that m is the mass of the central object. That's another important point here. One last thing, and this would actually apply to universal gravitation as well, but when we have those ratio problems, we want to make sure we square and cube all coefficients related to that. So, for example, if our radius is 3r, we put into our equation, it's really that entire quantity squared. So that entire quantity cubed. So 3r cubed, which would really be 9r cubed. So you have to cube the coefficient in addition to cubing the variable.